Yeah, B and C, again, I took these questions out of the test generator, and then I always, if I do that, I change the wording to make a little more sense to me. B and C really say the same thing, which I'm not showing it here, but B says summarize the results, and C says is there an association, and deciding if there's an association is summarizing the results, so they're kind of the same thing. But so I guarantee you there will be a question like this on the exam. Right? I will give you a contingency table, or I'll give you numbers and let you fill in a contingency table. But either way, you're going to have a contingency table, and then I'm going to ask you questions about it, proportions on there. I might say, what proportion of people sat in the front of the bus? Well, that's not being asked here, but I will do that. Okay? What proportion sit in the front of the bus? And how would you compute that? Okay, you need to get a total, right? You need to get the row totals. What I'm going to do is I'm going to lower that table down so I can write on it. So we need the row totals out here. So what is 58 plus 870? 928. Okay, and 166 plus 1163? 1329. And the bottom one, 193 plus 806? 999. Okay. Now let's go ahead and down here we'll put the grand total. So sum those three numbers. It'll tell me how many people total were surveyed. 30 what?
3256.
3256. Okay? So if I ask you a question like, what percent of people sat in the front of the bus, what two numbers do you divide? 928 divided by 3256. Right? Now what they ask is create a side-by-side bar graph that compares the three seat positions with respect to nausea stats. What the heck is that going to look like?
Wouldn't it look like this graph on the sulfur, the emissions? Like the
It would, except we want bars for nausea and bars for no nausea side by side. Or another way to do side by side that I showed was where you have one histogram and then underneath it another histogram. I did males and females that way, some stuff like that, and that would be acceptable also. The way that I'd probably set this up is I would probably go nausea and no nausea, and then go front, middle, rear, front, middle, rear. Now the other way you could set it up to be just as good is to go the other way. Front, middle, rear, and then go nausea, no, nausea, no, and so on. And you'd be graphing the same exact numbers, just organizing the bars differently. But I like this one because it puts the numbers that I want to compare right next to each other. So what's being implied here but never said is that you need conditional proportions to be able to compare. So what's the proportion of what that you're going to be most interested in? Whether they were nauseated or not. I want to know the proportion of people who were nauseated, conditioning on where they sat. So I want to do row proportions. I had 928 people who sat in the front of the bus. What percent of them got nauseated? So I'm going to write those conditional proportions out here. 58 out of 928. Somebody give me that as a decimal. .056?
Yes. 0625.
I was gonna say, that's not the number I had memorized.
You did 52.
You did 52,
Yeah.
okay. So 0625. The next one is for the middle, 166 out of 1329. And that's .12 something, 1249. If anybody disagrees with these numbers, just holler, because sometimes we get them wrong. The last one is 193 out of 806, which is 19 something, right?
Yeah.
Oh, yes, thank you. I was just seeing if you were watching. 999. 0.1932. Okay? So these are conditional proportions. When I say them, I'll say them as percents. People who sat in the front of the bus, 6% of them got sick. In the middle of the bus, 12.5% got sick. At the back of the bus, 19% got sick. So do you see a trend? The further back in the bus you go, the more likely you are to puke. Right? It's kind of a nice way to think about it. Now we'll plot those numbers. They are proportions for nausea. So it would go, there's 6%, there's 12%, and there's 19%. And that's really all you need, because what do you know about these bars? They're going to be the, I don't know what the word is, complement. If 6% got sick, then how many didn't? 94%. So if this one's 6%, this one's going to be 94%. And it's 0625, so it's going to be 0.9375. So you can get them by subtraction. So it's redundant information, but this is what the key wants you to do, is to plot these. And these bars aren't tall enough. If this is 19%, then 100% is up there, right? So 94%. So I'm not drawing them really to scale here, but
When you're writing the scale on the side, is there an easier way to do that as opposed to just going all the way to 100, or?
yeah, in this case, you about do have to go all the way to 100 if you put these tall bars in there. But otherwise, you don't have to go to 100. If you only had these three bars and the top one was at 19, I'd probably stop at 20.
Right, but if on the test we have one, we have to go all the way up. Is there an easier, more painless way to number?
No, just divide them into fairly even things and say, well, this is 10% and 20%, 30%, and then just get close. It doesn't have to be exact. Yeah.
If in the case that we had to do the whole thing, could we, to space it out more, could we go up to 20, go up a little further, do the little jagged cut line, and then start at a higher number?
Yeah, you could do that sort of thing, but
I meant like on the left, on the
yeah.
right.
That's fine. In this case, it's not misleading to do that. Sometimes when people do that, they're being misleading. They're trying to magnify very tiny
Well,
differences.
you go over to the left and you go 10, 20, you go up a little further.
Yeah,
and
you do this.
Then you can put like 80.
And then go 80 like that. Yeah, that'd be fine.
Of course, the rear would be below it, so that wouldn't work well.
Yeah. Okay, last one, or last two, summarize the results, and then is there an association? And like I said, those are kind of the same question. Do you think there's an association?
Yes.
Yeah, it's pretty clear. There's a very obvious trend that, in fact, the percent of people doubled, right? It went 6 to 12, and then it went up again by that same amount, went up by another 6% or 7%. So yeah, very clear association. What would it look like if there was no association? What would this graph look like? It wouldn't necessarily look random, but what would be even?
The top of the bar.
Yeah, these would all kind of be roughly the same. Like that. So it didn't matter where you sat, about the same proportion of people got sick. And then these would all be about the same height. So that's what it looked like if there was no association. Okay? The last one on the test is the one about coal and the density of the coal and the percent ash. And I'm starting to worry about time a little bit here, so I'm going to go through this as quick as possible, but I can also guarantee you you'll have a problem like this on the test. I'll give you some data, and you got to realize, oh, this is a regression problem where I need to put the data in my calculator, come up with the equation of the line, come up with the correlation coefficient, and then make interpretations over it. So what we have is the density of coal that's mined out of the ground. The density ranges from 1.25 up to 1.55. The ash goes from 1.9% up to 23% of it is ash, which is not usable, doesn't burn. First one says construct a scatter plot to show the percentage of ash depends on the density of the coal particle. What's your strategy there? Okay, first define what's X and what's Y. What's explanatory, what's response? Well, it's kind of hard to tell here. If I were to figure it out just based on what I know about coal, which is almost none, but density of a rock and ash, I would think that the amount of ash in the rock kind of helps determine how dense it is, right? But they really say it the other way around. Right here's the tip-off. Okay, here's the clue. Scatter plot to show how percentage of ash depends on density. So what is that saying? The density is X. Percent ash is the Y variable. The percent ash is going to depend on what value of X. Okay? So we always say the explanatory variable is independent. The response variable is the dependent variable. Okay? So I'm going to put my X variable density into L1 and my Y variable ash into L2. So let me go to my calculator. And I'll go stat and then edit. And I have those 5 data points already entered into the calculator. Okay? So if you don't have them in yours, go ahead and get them in there. Now to do a scatter plot, there are instructions in that PowerPoint presentation that I posted out there on my courses that show how to do this stat plot. You're going to push second function and then this Y equal button. And it says in blue right above it, stat plot. So, second function, stat plot. Select the first plot. Just always select the first plot. Don't try to get more than one plot going or you'll end up confusing everything. Select the word on if it's not already. And then arrow down to type and select the scatter plot type, which is the first one. If I select the one next to it, then you can actually see it. See how it looks like axes and some dots? So that's a scatter plot. So select that one. Then tell it where your X variable is and where your Y variable is. It says X list L1, Y list L2. And that is correct for the way I entered the data, so I don't have to change it. But you might have to change yours. Mark means what symbol are we going to mark the points with on the graph. And I don't care what you use there. To get the graph, click on the zoom button. Instead of the graph button, click on the zoom button. And go down to the 9th one, which is zoom stat. And there's your scatter plot. Okay? There's no numbers on the scatter plot, so if you want to see numbers, you got to push the trace button and arrow around, and it'll tell you the coordinates of points. That's the best it can do. The first question, part A, says, does there appear to be a linear relationship? Yeah. Would you say it's weak, moderate, or strong? Very strong. What do you think the R is going to be, the correlation coefficient? close to 1. It's going to be real close to 1. In fact, I would guess it's 0.99, something around there. So let me go back to the test and see what question I'm supposed to answer. What is the correlation coefficient? Oh, no, I forgot this. Part B. By inspection, do you think there's any outliers in the data? If so, circle them. Did it look like there were any real outliers? No, it really didn't. So in this case, you'd say no. That's an easy question. Then use the calculator to answer the following. What is the correlation coefficient? So where do I go to get the correlation coefficient? Okay, I push the stat button, and then test, and then stat button, test, and then down to Lin-Reg t-test. Okay. And then it wants to know, where is your X list, where is your Y list? They should already be set if you did the scatter plot. What about the next line? The freak, the beta, the reg EQ.
No, such thing.
Just ignore those. Yeah, don't mess them up. Just arrow past them and just go down and hit calculator. And it gives me a bunch of information that I can ignore, but then starting with A, I'm going to need that information, and then the correlation coefficient is all the way to the bottom. So let me arrow down to it, start off with. So R is 0.991. So like we said, very strong correlation. Next question says, give the equation of the regression line. So how do I get the equation of the regression line out of this? Okay. Now let me arrow up. I got to arrow up 1 to see the A. There it is. So y hat, at the top it says y is A plus bx. My A is negative 91.74. If I go to 2 decimal places. My B is 73. 73.75 times x. Now it's helpful if you'll label what x and y are. So x was density and y was ash. Okay? So there's the equation of the line. That gets you full credit on that question. Now it's going to say, what do the numbers A and B represent in terms of density and ash? So if I say, what does A represent? What's your answer to that?
When there's a ash percent of 0.
Okay, ash is the y variable. So when there's a density of 0, you get an ash of negative 91.74. Okay? So the A is always the y-intercept, but don't just say that. It's the value of whatever your y variable is when whatever your x variable is 0. Okay? Now negative 91.74 doesn't make a lot of sense. This is percent ash. You can't have a negative percent. But you also shouldn't extrapolate your line all the way back to 0 because you don't have data anywhere near 0. So, yeah.
Sorry, can you just repeat that? Like what's 0?
Your x variable.
When density is 0, this number is the predicted amount of ash. Okay?
So when, you always say when x is 0.
Right. But don't say x. Say whatever your x variable actually is. Okay? And then what's 73.75?
Slope.
It is the slope, but that won't get you any credit.
For every 1% increase.
You're switching your x and y around again. It's for every 1 unit increase in the density, And I think the unit of that was grams, right? The density was grams per cubic centimeter. So for every 1 gram increase in density, you'll get a 73% increase in ash. Now again, if you think about the numbers, and you always should, that seems huge. Just change by 1 unit, it goes up 73%. So when I change 2 units, I'm already over 100%. But if you look at the data, what is the data range for X? Does it ever change by a whole unit? No, it never even changes by a half a unit, right? So interpretations can be funny like that, but that's what it is. Okay, what's the next question?
Proportional reduction in error.
What's the proportional reduction in error you get by using the regression line to make predictions?
R squared, right?
That's the R-squared value. Proportional reduction in prediction error. Now another definition for that I gave in class, but it's not in the book, is it's the proportion of the variability in Y that can be explained by X. So it's the proportion of variability in ash that can be explained by how dense the coal is. Okay. And when I square 0.991, I get R squared equal, and this comes out of the calculator, 0.98 something, I don't remember what it was, but 27. So you say 98% of the variability in ash can be explained by the density of the rock. Or you get a 98% reduction in your prediction error if you use the line to predict. Okay? And looks like I'm out of time, but let's just hurry here. What is the predicted percentage of ash when the density is 1.25? How do I get that?
You plug it into the equation.
I plug 1.25 in there for X. Somebody just give me that number. 0.44 what? 75. And then it says, what's the residual? So how do you do residual?
If it's the actual data, y minus 1.
It's the actual Y minus the predicted Y. And the actual Y, you just look at the data set and see, well, what was the Y value for the one that had 1.25? And it was what? 1.93. So I get 1.93 minus 0.4475. So whatever that number is, that's your residual. Okay? All right, that's it. Good luck studying. Make sure that you let me know if you have any questions between now and then. And we'll see you at noon. Usually I let people come early or stay late, but we have a class in here before, so we can't come early, but I don't know if there's a class coming in right after, but plan to be ready to do it within an hour. Okay?
And you'll have the rest of the answers for tonight.
24?
I wanna do the last part of 23 too.
Yeah, actually, I have
Yeah,
that too.
C.
24, or 23.
Okay. We'll do 23 and we'll do it all, and then we'll do all of 24. Let me scroll just a little bit more and we'll be able to see part C above that band. There we go. Okay, this is a ball bearing question. The process of manufacturing ball bearing results in weights that are approximately normal, have an approximately normal distribution with a mean of 0.15 grams and a standard deviation of 0.003. Part A says, suppose you select one ball bearing at random. What's the probability that it weighs less than 0.148? Now, like all of these kind of problems, the first thing you got to do is figure out what kind of a problem is this. The last one we were just working on, that was a probability problem, and you have to think, well, okay, that's a probability problem where they're giving me numbers to fill into a table or a tree diagram or something, and I just use my rules for probability. This is what I call a probability rules type problem. What kind of a problem is this one? A calculator one specifically? A normal distribution calculator problem, right? So this is going to be either normal CDF or inverse norm, or both. And it is actually both when you go through all the parts. So that tip-off is where it says approximately normal distribution. If you see that in there, you start thinking normal CDF or inverse norm. It's got to be one of those two things. Now, how do you know which it is? What do you use normal CDF for? Unknown probabilities. If they ask you to find the probability of something, then that's normal CDF. If they ask you to find a value that has a given probability, then that's inverse norm. So part A, which is that? What is the probability that it weighs less than 0.148? That's normal CDF because it's an unknown probability. So we want normal CDF. Now most of you, at least until I slap you upside the head, will go straight to your calculator and grab that thing and start punching in numbers. What do I want you to do first? Draw the picture. Thank you. Draw the picture. So I'm going to draw, there's my axis, that shadow. So here's my picture. It's centered at what? 0.15. And halfway down the hill, on each side, is one standard deviation. And they tell me that one standard deviation is 0.003. So that's 0.147 to that side and 0.153 to that side. Right? Now, next thing you do is draw the region they want the probability for and shade it. What does it say? Probability that it weighs less than 0.148. So 0.148 is a third of the way from 147 to 1.5. So about a third of the way, it's about right there. What's the next thing I always make you do? We're still not going to go to the calculator. Before you do that, what do I want you to do?
Figure out how much that part.
Figure about how much it ought to be. Get a ballpark estimate. Okay. Well, if it was at the dotted line shaded down, I know that number. What would that be?
144.
Close, but no, it's a little bigger than that.
One standard deviation.
0.16, right? Because 68% is between the dotted lines. What?
I was just saying 30.32 divided
Yeah.
by 2.
0.32 divided by 2. You have 68% in the middle, which means 32% is outside of there, and half of it's down here. So I know that my answer is going to be bigger than 0.16. And a fair amount bigger because it's a third of the way on up there. So I'm going to guess 0.2. Is that good? All right, so I'm guessing ballpark BP equal 0.20. If I get an answer that's way different, then I did something wrong. If I get an answer that's close to that, then I can feel confident and go on to the next problem. Okay, so now, normal CDF, you enter 4 things. And what are those 4 things?
Left
Left,
and right.
right, mean, standard deviation. So left edge of my shaded region.
Negative 0.99.
There is no left edge, so it's negative infinity, negative 9999, and that's plenty of 9s when your values are decimals less than 0. Right? So then I go up to 0.147 is the right edge of the shaded region, and then mean and standard deviation. 0.15, 0.003. Okay? Punch that into your calculator and tell me what you get. You got it, Delaney?
5.25 written down, the figures from earlier, so.
Well, it is 0.25 something. I just don't remember what. Give me 2 more places. I always like to go 4 places on probabilities.
1587.
You forgot the decimal in front of the 0.999. Don't you have to write negative 0.9999?
This?
Yeah.
If I put negative point, that's a common mistake actually. No, you don't ever put a decimal in front of the 9s. Even though there's decimals in front of the rest of them, what is negative 0.9999? it's about -1, right? Which in this problem is going to work okay. But think if you were going to infinity and you put 0.9999 instead of 9999, that's 1, right? So you're going up to 1, and that'll screw things up. So don't ever put that decimal on your infinity, okay?
But when I didn't put the decimal in, I got 0.158.
Yeah, that's what I'm getting now.
So it says, isn't the right number supposed to be 0.148?
Yeah,
Yes.
That
so-
was my question.
Thank you.
Yeah.
It's because I never wrote the 148 down here, so when I glanced down, I put in one. I drew the line at 148, but then I didn't write it. So that number should have been 148. The number you got, by the way, was pretty close to 0.16, right? Which we already knew what that would be. But now it should be a number bigger than that, which
0.2525.
2525. Okay? Yeah.
I just wanted to clarify, when you use -9999, it's when you don't have a lower number?
Right.
You don't, okay.
Yep. When you don't have a lower number, you enter negative infinity. When you don't have an upper number, you enter positive infinity. Okay? All right. We can use the same picture to do part B. What is the 95th percentile of weights of ball bearings? First thing I want you to do is I want you to draw this picture and label where you think it's going to be. And 95th percentile, you should be somewhere close to 2 standard deviations on which side? Above or below the mean? Above. So 2 standard deviations would take me to 0.156. And I'm not very accurate on my drawing here. I left that tail way too big. It should be more like that. So the actual value that I'm going to get back, I'm going to call it x for now, because I don't know what it is. Just call it x. Is it going to be in here or out there? Slightly inside of 156 or slightly outside of 156? Who said that? What'd you say?
As a slightly inside,
Slightly inside, that's right. And why? How'd you know that?
because that'd be like 96% and look 95.
Yeah, because this would be 2.5% out here, right? Which leaves 97.5% below this. So 156 is the 97.5 percentile, however you're supposed to say that. So 95th percentile needs to be this way just a little bit. So draw it right in there. That's my x. So I know that if I get a number that's in that region, 0.15 something and fairly close to 156, then I got it right. If I get something bizarre that doesn't seem to make sense, then I know to go back and check my work. This is an inverse norm problem. So x is inverse norm of point what? 0.95. You enter the percentile that you want, the area below the x. Okay, so the area from negative infinity up to x, and that's going to be 0.95, and then just the mean and the standard deviation. Tell me what you get. 0.1549. Does that look like where it should be? Yeah. Now, just for fun, go back to your calculator and enter 0.05 instead of 0.95. Let's pretend you got confused. Am I supposed to subtract that from 1 or not? Because sometimes we do that if they give us the area above. What if you put in 0.05? What number do you get here?
0.1451.
0.1451. Could that be correct? If you draw your picture accurately, you can immediately go, well, that can't be right, because 145 is down here. 95% of this distribution is not below a number over here. You have to be way up here to get 95%. So immediately go, oh, I did something wrong. Well, let me try 0.95 instead of 0.05, and oh yeah, that looks better. Okay? So learn to catch your own mistakes. Part C is a little bit trickier, but it's the same idea. Now they want a number x such that 90% of the ball bearings will have weights between the mean minus x and the mean plus x. So this is really similar to those problems where they said how many standard deviations do you have to go on each side in order to get 90% or whatever. Right? So I don't care about that number x just yet. What I'm going to do is I'm going to say, well, on my figure, I need a left edge L and a right edge. Actually, it's probably going to be that same number, so I'll just leave it there. I need a right edge so that in between those two numbers is 0.90. You don't need to find both L and R. You find one of them and you can answer the question of what this x is just by subtraction. So I think L is probably the easiest one to go for. So I'm going to say L is equal to inverse norm, and you enter what number there? It's supposed to be the area that is left of L, from negative infinity up to L. How much is that? Morgan, you're kind of frowning. How much is in between here? Give you a hint, I wrote it right there.
So 90 minus.
So how much is not in between here? 0.10, and half of that 0.10 is up there, so 0.05. See the thought process? So it's 0.05 is to the left of L. And then again, it's just mean and standard deviation. So L is what number? Somebody got it?
0.1451.
1451, which is exactly the number you got a minute ago when I said, what are you going to, suppose we made this mistake. Now how do I use this number to solve for x? Well, I know that this whole thing is my L, 0.15 minus x. So 0.15 minus x is equal to that number. So now I just algebraically solve for x. So it's just the difference between 0.1451 and 0.15. And what is that difference? 0.0049. So x is 0.0049. And you're done. You don't need to go to get the R number at all. Because by symmetry, it has to be the same. All right. It's not the same, but it gives you the same x. Yeah.
I guess I don't get when you don't use the normal CDF and when you don't use inverse.
Okay. When to use normal CDF, when to use inverse norm. Use normal CDF if they give you values and ask for a probability. So I call these unknown probability problems. Inverse norm, they give you what? They give you a probability, like 90% of the ball bearings, and they ask for a value. So I call these unknown value problems. So if they ask for a probability, use normal CDF. If they ask for a value with a given probability, use inverse norm. Okay, next question.
24.
Oh yeah, I forgot, we already had that one in the queue. 24. The online access computer service industry is growing at an extraordinary rate. Current estimates suggest that 20% of people in the United States with home-based computers have access to online services. Suppose that 15 people with home-based computers were randomly and independently sampled. What is the probability that at least one of those sampled have access to online services at home? Now this is an outdated problem. I suspect that people with home computers, way more than 20% of them have internet access. But you know, if this was even just 10 years old, that probably would have been fairly accurate. But today, I bet that number is closer to 95%. Or even my mom has internet access. And if you knew my mom. Okay, so how are we going to work this problem? This is another one of those where you get that shudder, isn't it? Like, oh God, there's just all kinds of information in there. The first thing you should do is figure out what kind of a problem is this. Is it a normal distribution problem? Does it ever say in there, are approximately normally distributed? Nope, so it's not a normal distribution problem.
I know.
What, I heard somebody say binomial. How do you tell if it's a binomial? Well, the first thing you check for is whether you are counting the number of successes in a fixed number of trials. Right? That's condition 0. Is that happening here? Are we counting the number of successes in a fixed number of trials?
Yeah. Online is a success, having online service.
Okay, having online services is a success, and what is my fixed number of trials? 15. I'm going to sample 15 people, and each of those people either has online access or they don't. Right? So I'm counting the number of successes in a sample of 15, a fixed number of trials. So it meets that condition. Now, it still might not be binomial. You still have to check the rest of the conditions. And what are they? Okay, they have to be independent. Are these independent? Are these 15 people independent? It says independently and independently sampled.
Equally
Right?
likely.
What's that?
It has to be equally likely
Exactly.
each trial.
Each trial has to be equally likely. You have to have the same probability of success on each of the 15 trials. Is that going to be the case here? Technically, no. But practically, yes. Technically, no, because when you draw a survey, you sample without replacement, right? So if there are 100 million people in the population who have a home-based computer, and you sample 15 of them, technically, when you get one person that has online access, there's one less in the population to select, so the probability changes very, very slightly. And what does the author say about that? He says, don't worry about it as long as less than 10% of the population. And I'm taking 15 people out of the whole United States. That's way less than 10% of the population. So the answer is technically no, but don't worry about it. We're sampling less than 10%. So yeah, the probability stays essentially the same. So we meet that condition. And if that condition's met, the independent condition is automatically met. That's the third one. Are they independent? We already talked about that one. It says independently sampled. So we're good to go with binomial. This is a binomial problem. Right? Well, knowing it's a binomial problem, first thing you should do is figure out what is my n and what is my p. N we already talked about. Number of trials. What is it? 15. P is probability of success on each trial. And that's 20% or 0.20. Now what they ask is, what is the probability that at least one of those sampled have online access? Probability of at least one. How do I write at least one as a mathematical statement?
Greater than 1.
Probability that x is greater than or equal to 1. Now we know it's a binomial problem, and I have a greater than or equal to 1. You remember that, let's see, I guess I'll write it over here. Remember, I had this on the board last time. If it asks you exactly equal to something, that's a PDF. Binom PDF NPX. If it's a probability x greater than or equal to little x, it's binom CDF at NPX. This one doesn't match either of those. It's a greater than or equal. So what do we do?
1 minus.
1 minus. We have to do a complementary event kind of thing. So the probability, I'm going to get a little more room here. Probability that x is greater than or equal to some little x is equal to 1 minus the probability that x is less than or equal to little x minus 1. And it's the minus 1 because it's a complementary event, right? If you didn't get at least 1, you must have gotten 0, right? Less than 1, and the only whole number that's less than 1 is 0. So I have to subtract off from 1 minus 1 gives me my 0. Okay? And then this is 1 minus binom CDF from n, p, and little x minus 1. So, here we go. 1 minus the probability that x is less than or equal to 0. Now, when it's a 1 and a 0, you really don't have to have the less than part because this is counting data, right? We're counting number of successes. You can't have a count less than 0. But just because it'll match what I wrote there, I'm going to leave the less than or equal. Doesn't hurt anything. And then I can still use the binom CDF. And binom CDF or PDF would either one give the same answer in this case because it is a 0. N is 15, P is 0.2, 0.20, which you don't need the O, and then 0. Tell me what you get as an answer there.
9648.
Okay. Anybody else?
0.0352.
I was hoping somebody would say that. What she said, and this is what happened in the last
Oh, I
class.
forgot that.
0.03, what'd you say, 0.0352?
Oh, 0.0352.
And somebody, the first person that answered last time in my previous class said that number, and I looked at it and I thought, that doesn't seem right to me. And I want you to get good at that. I want you to get good at knowing, well, that doesn't seem like that should work. Why does that number seem too small? If I take a sample of size 1, what's the probability that I get at least 1 success in this problem? What's the probability that a randomly selected person has online service? 0.2, 20% of them, right? So even if my sample size was just 1, I have a 20% chance of getting at least 1 success. Now if I take 15 people, I ought to get a really big number for that probability. At least 1 success out of 15. When each of them has a 20% chance, I should get a number up close to 1. When I get a number that's down close to 0, I'm thinking, oh, I forgot the 1 minus part, right, Chelsea?
Yeah.
So it's 1 minus that number, which somebody else said was 0.99648. That's a number that I can live with. I can look at that answer and go, yeah, I expect it to be a pretty high probability. I probably got that one right. I'll go on to the next one.
Mine keeps saying error, I can't put mine in right, I guess.
Yeah, I did that. Mine got that when I did the 1 in front the first time after my wrong one.
I don't know what you got going. You entered these, all 3 of these numbers?
Then I did 1 minus and then did my second bar.
Yeah, that should be okay.
And then I go down and I do binom CDF, right?
Uh-huh.
Okay. Kind of give me a little thing.
And then
I go
15.
15. Oh, maybe, I think I put 0.15.
Ah, yeah, everyone doesn't like that. It's got to have whole numbers.
Got it.
Okay? Now notice the distractor A here. It's that mistake. So the common mistakes, there's 2 really common mistakes here. One is forgetting the 1 minus. So in your notes you might want to circle that or something and say, be careful. And then the other one is this. A lot of people will make the mistake, they'll do the 1 minus thing, but they'll put a 1 right there instead of a 0. They'll forget to subtract 1 off. And that's the wrong answer.
How do you get to the 0? Like, why do you use 0?
Don't try to memorize formulas. I wrote a formula for it here, but I always discourage people from memorizing formulas. Try to think it through, okay? What is the complement to at least 1? What does that mean? I want you to answer the question out loud. If you didn't get at least 1 success, how many successes did you get? 0. That's why it's a 0.
How do you know to use the complement?
Because my calculator won't do a greater than. But I know, well, I can make it a less than by doing the complement, and that my calculator will do. If we had a binomial function that did the greater than or equal, we wouldn't have to use the complement. But I just know the limitations of my calculator, so I need to turn it around and make it a less than or equal to by using the complementary bit. Yep.
Wait, if you had something like, instead of saying at least one, you had at least three, would the complement be two or less?
Yep, exactly. And that's what this says. If this was a 3, then the complement would be less than or equal to 2. Okay? So if this was a 10, which I think's the next part, nope, it's down here. Find the probability of 10 or more of those sampled. What is 10 or more? How do I write that? Greater than or equal to 10, right? 10 or more. At least 10 is the same thing as 10 or more. So they're just trying to confuse you. So if that's a 10, then this is a 9. Because the complement to 10 or more is 9 or less. Okay?
What,
Go ahead.
I was just gonna ask for number 25 too, how would you write that one?
Yeah, I was just going to do that too. Now, 25 here, it asks for the mean and the standard deviation. If it's binomial, and only if it's binomial, you got a really simple formula. What's the mean? Mu sub x. N times p. So in this case, that's 15 times 0.2, which is something, 0.3? 20% of 15 would be 3, right? Is that 3?
Yeah.
Okay. And then sigma x, the standard deviation, is the square root of n times p times 1 minus p. So you just plug it all in. You got 15 times 0.2 times 0.8.
So we should memorize those ones?
Memorization is a terrible word. You should write them on your cheat sheet.
Okay.
But yeah, definitely have those on your cheat sheet. This one is intuitive, right? This one makes sense, but the standard deviation, there's no intuition there.
I just forgot about that.
Two questions. I can't remember, what's the exclamation point thing called?
Factorial?
Factorial. Should we write the x
No.
factorial over here?
No, I won't make you use that. It's
Okay.
built in. I use it when I lecture on it to teach what the calculator is doing. You know, it has the binomial formula built into it, and it has this factorial thing. But we're just going to use binom CDF, binom PDF. It's built in.
That's probably what I should have used on the phone, but
Yeah.
I just did. I typed all that factorial stuff into my calculator. It took a while.
Yeah, and if you get a big sample, like instead of 15, if you get to 100, your calculator will say overflow error because it can't handle 100 factorial. Okay, next question. Jory?
On number 27, after you find the missing probability, you can just do that by 1 minus all those added together, right?
Right.
Okay, and then it says compute the mean. Would you use the n times p again to find the mean?
Nope,
Or
it's
how
not
would you-
binomial. How do I know it's not binomial? Well, I don't really know except that, well, I know it's not binomial because I'm not counting successes in a fixed number of trials, right? So I just have a probability distribution, a discrete probability distribution. So once you find the missing probability, how would you find mean and standard deviation? You put the x's into L1.
Oh, okay.
So I'm going to draw arrows like this. Those go into L1, these go into L2, and then you do what?
Second bars.
One bar stat,
Yeah.
L1, comma, L2.
Okay, well now that I remember how to do it.
Okay? Now there is a little bit of a trick on this one because it says 4 or more. It doesn't say just 4. But on the key you'll see that I used just a plain old 4. You had one in the homework like that and they had you put in 4.5 for that one. And it's, you know, it's sort of arbitrary what you put in for that one catch-all something or more. And it depends on if you don't think there'll be very many more than that, then you just use that number. If you think it'll be barely more than that, then use 4 point something. But if you think, well, that could go all the way up to 20, maybe I'll stick a 6 in there. And you make a choice. Okay, that's all the time we have. I will go back over to my office right now and post the key to this so you can get the rest of them answered that you didn't know. But feel free to email me with any questions that you have over any of them. That even though you have the key, doesn't necessarily mean you understand why that's the answer. Right? So make sure you let me know. And we will see you Wednesday with your thinking caps on.